All right, now we want to focus on if we have data points and we have a model, how do we actually find that best fit line? How do we find beta naught and beta 1? Now, one thing to note here is we have eyes on in our model now. So this is representing that we have data to match our model. For example, this individual here would be x1 and y1. This individual here would be x2, y2. And each of these individuals represents this different yi and xi. All right, and what we want to do is a method called Ols, Ordinary Least-Squares, and that's going to help us get this best fit line. Because what we want is to put a line through this data, and we want to take this line and make it the best fit by doing what's called minimizing the sum of squared errors. So for each of these individuals, so this distance here between the dot and this best fit line, that's U1. That's for that person. To take this distance here, that's U2. And each of these individuals is going to have a distance from the data point to their line. And our goal, so each of these is UI, is we want to take all of those and we want to minimize the sum of squared errors. Okay, so the way we do that is we write yi, and we rewrite this term, our model, in terms of ui. So ui is equal to yi minus beta naught minus beta 1 xi. Okay, and so now we want to take the sum of the squared errors. So we want to square this. So I square that u there, so that means I have to square this side. And I want to take the summation of each side, and now I want to minimize this. Now, to minimize this, we want to take derivatives and set them equal to 0. And so what we're trying to do is we're trying to choose not x and y, but we're trying to choose beta naught, which is our intercept, and our beta 1, such as to minimize this line. And so what we do here, and I'm just going to write this out in the lecture notes, it goes into more detail of actually how to solve this, is we're going to take the partial derivative of ui squared with respect to beta naught. So we're saying let's let beta naught change such that we get this best fit line. So let's let the intercept go up and down until we get that best fit line. And so we're going to set that equal to 0 because we're minimizing. Remember, if we take the max or min, we take the first derivative, set it equal to 0. Now we go to the next one, is it's not just choosing the intercept, but we're also choosing the slope. So that means I take the partial derivative with respect to beta 1 and set that equal to 0. So I'm choosing beta naught and beta 1 such as to get this best fit line to minimize those errors. And by doing that, what I get is beta naught hat. So now the hat comes on because I'm using data to estimate that best fit line. So now I actually have that best fit line, so that beta naught is equal to, and this is just an equation that I get from using this method here, y bar minus beta 1 hat x bar. And the way I get this one right here, beta 1 hat, which is the estimated slope of using the data to find that best fit line slope, is equal to the summation of xi minus x bar times yi minus y bar all over xi minus x bar squared. Okay, so that's how I find beta 1 hat and beta naught hat. Now another way I can write this is the covariance between x and y over the variance of x. Okay, so that's just what that equation means. So now the question is, how do I actually go about using this to find the data? Well, for each individual xi, for all the x's, I can find the average x. Okay, so x bar is equal to 1 over n summation of xi. So I add up all of my xi's and I divide it by n. Y bar is similar. I add up all my yi's and divide it by n. So that's how I get x bar and xn. Now, for each of these, what I want to do is take xi. So let's assume that this is x bar, and this is y bar. So for each xi, so here's x1, I take x1 minus x bar, which would be that term. I take yi, so here's yi, minus y bar, and multiply those together. And that's just for the first person. And I do that for everybody, and that's how I get the numerator. To the denominator, I take my xi, which would be here, minus x bar, and then I square that, and then add it up for everybody. And that's how I actually get these exact numbers. And we'll show you in just a bit of how to do that in Excel. But this is what we call the ordinary least squared, and it's designed to give us our beta naught and our beta 1. Now to reiterate, beta naught and beta 1, this is our model. There's no hats on it. But we actually don't know what beta naught and beta 1 are because we don't know the population. We don't know the true representation. So when we estimate it, this line now, the equation for this line is going to be beta naught hat plus beta 1 hat x. The u is going to drop off because we've minimized those errors, and we have this best fit line, y equals mx plus b. And that's what we do in ordinary least squared.